Hello, I'm Dr. Andy Hales at the University of Mississippi, and in this video we're going to look at how to do planned contrasts for a one-way ANOVA in R. So for starters, we're going to pick up this example from where we left off earlier. We've already run the one-way ANOVA, and we've saved it to an object called my_ANOVA, and we did that up here using the easy package. And we have our object here for the ANOVA. Our mission for now is to imagine that we'd planned ahead of time and pre-registered a set of planned contrasts to test specific hypotheses about the patterns of differences among these three means. Let's take a look at how to actually execute those planned contrasts. Now, in a moment, you'll see how we do this. But first, the code we're going to use cares about the order of these three levels. We have the control condition, the inclusion condition, and the phubbing condition. And R doesn't automatically know which of those is first, which of those is second, and which of those is third. So let's start by just asking R to give us a list of the levels of the condition variable. And if we do that, we get this response here, null. So not only do we not have them in the right order, R is actually saying there isn't any order to that. Now, why is that? Well, let's take a closer look at the condition column. We can use this str for structure function. And that tells us that the structure of this column, it's not a factor, it's a character. As far as R is concerned, these are just a bunch of strings. They don't have any order. Well, we want to tell R to put these in an order that's logical for us and will correspond to the contrast we're about to test below. And we have to do that explicitly. And the first thing we need to do is tell R, these aren't just characters, this is a factor. And it has specific levels that we can put in the order we want. So here we're going to make condition a factor. And once we've done that, we can ask R, okay, now that it's a factor, what are the levels of this? And R says, okay, it's a factor. The first level is phubbing, the second level is inclusion, and the third level is control. Okay, but we're going to test some hypotheses in a moment that require that the first two levels actually be the control condition, which is kind of logical to put first. Control is business as usual, so let's start with that. And then we want the inclusion condition next, and then we're going to need the phubbing condition to be last. So to reorder that, we're going to use factor relevel. We're going to tell it the name of the column we're releveling, and we're going to say first, the first level should be control, the second level should be inclusion, and the third level should be phubbing. So when we run this and check our levels again, we see we've got them in the order we want, conveniently corresponding to the order of our graph here. Control first, inclusion second, phubbing third. Okay, that was kind of tedious, but it was important groundwork. Now that we've done that, it's very straightforward to test our planned contrasts. We're going to use em means again, but this time we're going to pass the result of that onto this contrast command, and we're going to give it the name and specific codes corresponding to each of our planned contrasts. So here I arbitrarily called this PC_1 for planned contrast 1, PC_2 for planned contrast 2. And what I'm doing here is I'm imagining that we've planned and pre-registered that our first contrast wants to compare the average of the control and inclusion conditions combined to the average of the phubbing condition. That kind of makes a certain amount of sense. Being included is sort of the norm, it's what people expect. The control condition is also sort of business as usual. Phubbing is when something weird happens. So what we're doing when we combine these two together is we're sort of testing this business as usual. Anyone who wasn't phubbed gets combined into this cluster, and we're going to compare it to anyone who's in the condition where they were phubbed. And so the codes we're going to use to do that are -0.5, -0.5, and 1. Now, this is where it's nice to notice it really is critical that we put the levels in the order that we did. Otherwise, R would have no way of knowing that we want this negative 0.5 to correspond to the control condition, this negative 0.5 to correspond to the inclusion condition, and this 1 to correspond to the fubbing condition. But now that they're in the right order, and these are the codes we want to run, we're good to go for that first contrast. And notice our second contrast here is taking the control condition and the inclusion condition and asking if they're different from each other, and applying a 0 here to ignore the fubbing condition. So we're going to set fubbing aside and just ask, are the control and inclusion groups significantly different from each other? That's what the second planned contrast answers for us. And we're telling it to make this a two-tailed test here by setting side to equal. So when we run this, we get two results, one corresponding to each planned contrast. So first, we have our t-test and p-value for the contrast between the combined means of the control and inclusion condition compared to the fubbing condition. And we can see it's a very strong t-value, and the p-value is very, very significant, which matches what we can see with our own eyes looking at this graph, so that's what we'd expect. And then looking at the second planned contrast, we can see the effect is a lot smaller. The t ratio is just 1.5, and that is not statistically significant. So we don't have any evidence from these results that the control group is any different from the inclusion group. Cool. So that's how you do the hypothesis test. What we don't have here are standardized effect sizes. And when you're reporting the results of these specific mean comparisons following up on the ANOVA, it's good practice to include an effect size, and people usually expect to see a standardized effect size. So let's look at how to do this in this particular context. Now, you already know from earlier with t-tests, when you're comparing two groups, you'd use Cohen's d, and we use the f-size package to produce Cohen's d. But here, because we're looking at these specific clusters of means, we need to do a little bit of recoding of the data to tell it which particular clusters of means we want to compare to which others. So let's load up the f-size package, and let's start by computing Cohen's d for this first contrast, the pooled mean of the control and inclusion group compared to the fubbing group. And what we need to do here is a little bit of recoding. So what I'm going to do is I'm going to compute a new column called contrast 1, and I'm going to use case when. This is ordinary recoding. This is similar to what we did earlier when we were reverse scoring variables. So I'm telling it for cases when the condition is equal to control, we want to call that not fubbed. And for cases when the condition is equal to inclusion, we also want to call that not fubbed. And finally, when condition is equal to fubbing, we can leave that as fubbing. So what you can see is happening here is we're melting together the control and inclusion groups into one mega condition. So now, after doing this, contrast 1 has just two separate groups in it, anyone who is not fubbed and anyone who is fubbed. And now that we have just those two groups, we can use code from earlier to compute Cohen's d. So we're looking at, again, our dependent variable is recalled well-being, and we're predicting that from this dichotomous variable that we just computed. And when we, I have to actually run that. And when we do, we get Cohen's d, which we can see is just a cartoonishly large 2.29 is the difference between anyone who wasn't fubbed and anyone who was fubbed. Cool. So to get the Cohen's d for our second planned contrast, where we're comparing just the control condition to just the inclusion condition, we also have to create a new column here, and we'll call this contrast 2. And for contrast 2, we want to get rid of the fubbing condition because that wasn't a part of this contrast. We're only comparing the red bar and the green bar here. And so to do that, we're going to use case when again, and we're going to tell it you can keep the control condition the same as the control condition. Inclusion is still inclusion again, but anyone who is fubbed, we're just going to set that to missing so that it doesn't participate in this contrast and doesn't go into the effect size that we're about to compute here. So when we run this and compute the Cohen's d for contrast 2, comparing control versus included, we calculate that the Cohen's d is 0.56. So there you go. That's how you compute both the planned contrasts with the hypothesis tests and also the Cohen's d effect sizes for each of those planned contrasts. Earlier, we talked about how to do Tukey post-hoc comparisons. You can use similar methods, the tools we used here, to get Cohen's d for particular pairwise comparisons as well. So that's how you do planned contrasts in R. And next time we'll look at how to do power analysis for ANOVA.